Thank you very much. I'm actually a product of you. um, thank you for Professor D'Amico for inviting me to give this lecture today. And the topic, let's say, of the talk is multivariate data analysis. So I will talk in the next hour so on about, let's say, method to deal with the multivariate data analysis that occurs frequently with sensors and instruments. Okay, a few words from where I come. I come from the University of Rome Tor Vergata. And just to say where I'm interested in multivariate data analysis, I work on sensors, in particular on chemical sensors, and we design receptors. We apply receptors to transducers. We put the sensors together to make, let's say, sensor arrays that work mimicking the olfaction and taste. So we do, let's say, the so-called artificial olfaction and taste. So in this story, multivariate data analysis is an important part of to deal with this kind of instruments and to understand what we do and to understand which is the role of individual sensors in the sensor array. So I hope I will be able to convey this to you today. And this is, let's say, the outline of what I'm going to talk. Introduction about multivariate data, and then I will basically talk about three different aspects of multivariate data analysis: the visualization of multivariate data and what we can infer from this visualization, the regression, how we can, let's say, connect the multivariate data to, let's say, some specific objective, and the multivariate classification. There are, of course, a number of different algorithms or different methods to treat with the data. I will let's say, confine my presentation today to these two approaches, let's say, the principal component analysis and the partial least squares. That is, let's say, the basic. From that, then you can build to use even more, let's say, sophisticated algorithms. But these are particularly interesting because give you full control of what you do. So you can, let's say, not only get results, but you also can understand which is the role of each variable in your problem, and then to understand which of these variables are actually important or not. So from where multivariate come? They come from instrument, of course. So we have instrument that provides, let's say, not individual numbers, but provide arrays of numbers, typically the spectroscopic technique where we go, let's say, to measure the property of a sample with the light at different energy, and then we have the response of the material at different energy. Or gas chromatography is a typical technique in analytical chemistry, where we, let's say, decompose a complex mixture in air into different elements according to their elution time, namely the time that they take to travel along a capillary channel. Or a gas sensor array, namely, let's say, the use of different sensors, non-selective, and then we collect the data from each of them and form, let's say, a sequence of numbers that is, let's say, that has the same dimensionalities of the sensors that we have in the array. So there is, let's say, a number of sources of instruments that provide multivariate data. But nonetheless, even if we use, let's say, individual sensor, at the end, when we use sensors, we usually want to describe complex phenomena, and then we put together sensors to describe, let's say, something complex. Even if each individual sensor provides univariate data, usually what we do at the end, the objective of the sensor, the use of the sensor is to bring sensors together. For instance, if we want to appreciate the food quality, we need to measure several, let's say, components. If we want to, let's say, to describe the property of water, we need to measure a number of compounds and so on. Even if these are measured with univariate sensors, we need then to put them together, and then it is necessary to have some tool to deal with this data. And usually, let's say, we put this together to let's say, infer some overall properties of samples. For instance, in food, typically freshness or shelf life are typical objectives. This is an example of this pattern, probably very trivial, but anyway, we have water. In the label of water, we have a list of compounds, and then the water is identified in some sense by these compounds. They form pattern. We can visualize this pattern in a very simple way, for instance, as a histogram, and then we see that just the appearance of this histogram provide us, let's say, just a first information about the different kind of waters. But we want to do, let's say, something a little more sophisticated in terms of representation, not to limit ourselves to see the histogram, but to see how the data are related to each other. And again, when we have, let's say, a matrix of data, because we have different samples, each sample is let's say, measured by different, let's say, variable, let's say, different indicator. So typically, we have a bidimensional data structure when we have a multivariate data, but we'll see at the end that this structure, the dimensionality can also increase. So instead of matrix let's say square, we can have cubes and so on. We can represent this as a histogram, as we have seen, or we can visualize in this very simple way with a color bar. But there is one property that usually multivariate data have, and this is, let's say, the basic let's say, information that we are considering. The fact that okay, we can, let's say, display this data. Typically, what we do in data analysis is to assign each quantity to an axis in a Cartesian space. This is something that comes naturally to us because it's our geometrical, let's say, interpretation of the world to build, let's say, Cartesian space where we can, let's say, assign each variable to one variable, each axis, each dimension to one variable of our let's say, multivariate data. Of course, this representation is limited to 3 because this is what we can actually visualize, but this vector space can have, let's say, whatever dimension. So this is quite important. This is I say that this is something, let's say, straightforward to transform the data that we collect into points into a space. And in case, let's say, of multivariate data, this is also more interesting because we introduce the notion of distance that can, let's say, provide a measure of the similarities of of the differences between different samples. But there is a said effect that is quite important in this kind of data, namely the existence of correlation. So this is something quite common. I mean that when we take a measurement of something, even if we measure with sensors that are not absolutely correlated one each other, what we are measuring in a sample is, let's say, the properties of the sample itself, and this makes appear a certain degree of correlation. We can make, let's say, a very simple example. If we measure height and weight of people, these two quantities, of course, are by themselves independent one each other. But when we put them together into axes, we see, of course, that height and weight correlates. But this is because this is an internal property of what we are measuring. So what we are measuring, let's say, has some internal properties that is manifested in terms of correlation among the variables of the multivariate data. These have a very important consequences in terms of the geometry of the space, because if we have correlation, it means that when we go, let's say, to translate our multivariable data into a vector space, the data tends to occupy not the whole volume, but tend to occupy a subspace because of this correlation. So this means that we have, let's say, a number of variables in our multivariable data. These variables have a certain degree of correlation one each other. So we can, let's say, and due to this correlation, the data point tend to occupy, let's say, a space of reduced dimensionality. So in the visualization, we can actually exploit this property for the reduction of dimensionality. So we can represent the data even if they are pertaining to a vector space whose dimension are the number of sensors or the variables that we are using. We can represent them, let's say, in a space of reduced dimensionality, and this is because there is correlation. And so in this representation, we do at the same time reduction of dimensionality, and we can remove actually the correlation itself. And there is a number of these techniques. For instance, for linear models, it is just a projection from one basis to another. This means to find a different basis where it is possible, let's say, to decorrelate the variable and then to reduce the dimensionality. And principal component analysis is just one of these methods. This one is probably the best known, and also the method with the more consequences in terms of interpretation of the multivariate data. The principal component analysis are based, let's say, on the probability distribution of our data, and we know that usually experimental data are normally distributed, and this is also applied to the multivariate data. But in multivariate data, of course, we have something a little bit different in terms that the vector is simply the mean vector, and the covariance matrix and the variance is, let's say, becomes a matrix, is the covariance matrix. So with these two quantities, the mean and the variance, we can build, let's say, the multivariate Gaussian, and this multivariate Gaussian, of course, has basically the same functional behavior of the univariate normal distribution function, and you see here a shape of the function in case of the two variate data. So in case the multivariate data has a dimension 2. And the covariance matrix is the important subject of this story, because the covariance matrix carries, let's say, the correlation between the variables. Because if we have, let's say, the shape of the covariance matrix and the geometrical arrangement of the ellipsoid that is defined by the quadratic form of the generated by the covariance matrix, let's say, gives, let's say, an imprint of the correlation between the variables. Indeed, if we have the covariance matrix diagonal, this means that the variables are not correlated, and they may have, let's say, equal or different variances, but anyway, the axis identified by the variables of our multivariate data are actually the principal axis, the canonical axis of the ellipses. In case of correlation, of course, we have the non-diagonal terms that are actually the correlation coefficient, and these covariant and this, let's say, non-diagonal matrix gives rise to an ellipsoid that is not oriented according to the principal axis. So in terms of geometry is very the correlation is very simple. It just means to rotate the basis x and y, that is the natural basis, because these are actually the quantities that have been measured, into a different basis that coincides with the principal axis of the covariance matrix. And of course, these variables that are called factors are linear combination of the original variables. So this is the idea then, to introduce in the vector space describing the multivariate data, to introduce a new basis formed by two orthogonal vectors And these two vectors has the properties, let's say, in these two vectors, in this new basis, the covariance matrix is uncorrelated, and the ellipsoids of isovariance points are, let's say, can be written in a canonical form. And then this is a very simple, let's say, a very simple geometrical operation, and we know that these directions are the eigenvectors of the covariance matrix, of the covariance matrix generating the quadratic form, and the extension of the ellipses along these directions is described by the eigenvalues of the covariance matrix. So this is basically the principal component analysis. And the principal component analysis then identifies the principal directions of the covariance matrix, or better, or the ellipsoids associated to the covariance matrix, and in which cases this operation is actually meaningful. I mean, this is meaningful if the data are normally distributed. Indeed, if the data are normally distributed, and if the mean is 0, so this is easily achieved, let's say, subtracting the mean to each variable, we have that all the information about the multivariate data is contained in the covariance matrix. And working on the covariance matrix, decorrelating the covariance matrix actually give us the possibility to, let's say, completely describe our data from the basis, the natural basis that are, let's say, the variables that have been actually measured in a basis of new variables that are linear combination of them. These new variables are then the principal components, the principal axis of this ellipsoid. This ellipsoid, of course, in a high dimensional space, in more than 3, let's say, is an hyperellipsoid, but this can be easily calculated. And, and as I said, the variance along each principal component is proportional to the associated eigenvalue. So this means that this principal direction, this principal component are not equivalent. This means that there is a hierarchy in terms of variance, because most of the variance will be with the first principal component, then the second, then the third, and so on. And the contribution in terms of variance of each principal component is decreasing. So this is the basis, this is the ground for the diminution, for the description of the data in a space whose dimensionality are smaller than the dimensionality of the original space, the original vector space. But we'll see an example soon. Okay, this is, let's say a very simple cartoon about this illustration of the principal component. We have, let's say, the sensor space. For instance, let's suppose we have 2 sensors, just to make a plot, and each dot here is one sample that has been measured with sensor 1 and sensor 2, and then it corresponds to something, to some, let's say, sample, to some physical occurrence of something. And this defines, let's say, a covariance matrix of these two. Can be the covariance matrix is simply the product of the multivariate data times the transpose, and this is the ellipse associated to the covariance matrix. And this ellipse, of course, has, let's say, is not in its canonical form. It means the principal axes are not aligned with the basis of the space. So we have here 2 operations: mean subtraction, and when we subtract the mean, only the covariance remains in the hypothesis that the data are Gaussian, are distributed normally. And then the second operation is the rotation of the original basis in order to fit with this component. So very easily, it means that instead of sensor 1 and sensor 2, where the data are correlated, we represent the data in a space PC1, PC2, where the data are no more correlated. And these are exactly the same data. We have not lost nothing about the original data in terms of information. But what we have here is that now we have a hierarchy between the two variables. Here we had no hierarchy. I mean that sensor 1 and sensor 2 carried the same information. You see, you cannot say that one sensor is more important than the other, because let's say the variance of each variable is comparable, is the same. But when we go to the principal component space, this is no more the case. We have the PC1 as the largest variance, PC2 as the smallest variance. In the original data, these two information that carried by PC1 and PC2 were shared by the two sensors, because they were actually measuring something from 2 points of view, the point of view of the different sensors, but they captured, let's say, all the internal factors of the problem. In this case, we have a decomposition of these internal properties, and then this is measured by the eigenvalues of the covariance matrix. So one eigenvalue is much bigger than the other, and then this means that the variance carried by the associated direction is much greater than the other. And if one is much greater than the other, we can reduce the representation from dimension 2 to dimension 1. And in doing this, what we lose? We lose just the information carried by the highest, let's say, principal components. Okay? So this is basically the idea. We have the information carried about the sample, let's say, shared by each sensor. The principal component, in some sense, distillates this information among the principal components, and each principal component is uncorrelated from the others. This means that the variance that here is, let's say, correlated, here is no more correlated, but the content in terms of information is the same. There is, let's say, the same meaning in this data. What is the difference is that the PC1 and PC2 are no more observable, but they are linear combination of the original, let's say, variables. If let's say the variance carried by the PC1 is enough for us, we can reduce the space and have, let's say, the representation in a reduced dimension space. Okay? So, which is at the end what we can, let's say, get from a principal component analysis? We get two information, because here we have the coordinates, the coordinates of each data point in the new basis, and this is called score. But we have also how each individual, let's say, variable, original variable, contributes to PC1 and PC2, and this is called loadings. In terms of geometry, this means S1, S2, and S3 is the original space. We have, let's say, these black points here are the original data, and they are projected onto the space of PC1 and PC2. This means that we are basically taking, let's say, a projection from a three-dimensional space onto a plane. This is something that we do, and every time we take a picture, basically. We project the three-dimensional space onto a plane. And this is the projection are the scores, but we have also the second component, the loadings, because the loadings is the projection of the axis. So how the original axes are projected into this plane, and then which is the role that the original variable plays in defining this projection, and then in defining the representation. Then we'll see some examples, and probably this may become a little bit more clear. Okay, let's see an example of this. This is a very simple experiment, well, very simple. It's an experiment in food analysis, and this is an example where we have, let's say, a number of different pitches, so different cultivar of peaches and nectarines, you know, the fruit, and some parameters are measured of these fruits are basically sugars, sucrose, glucose, and fructose, and acids, malic and citric acid, and the pH. So we have basically that all the fruits are, let's say, represented by a string of data and an array of numbers, and each number is the result of one of the sensors. And then here we have, let's say, all the different cultivars, and we could be interested to see how these cultivars, let's say, are arranged according to the acidity and the sugar content, and which is the role, the mutual role of these sugars and acids in this kind of fruits. And we can see here the raw data, let's say, in a color bar system, in a color scale. And we have, let's say, another important issue when we put data together to form a multivariate data. So the range, the actual values. So you see that pH and sucrose are numerically larger than the others. So of course, any calculation we do here, these two quantities, pH and sucrose, overwhelms the others. And in order to remove this, let's say, fact that it is just due to the physical properties of each compound, the data are usually scaled in order to remove the mean, and we have seen that removing the mean leaves only the covariance matrix to represent the data, and also to normalize, let's say, the dispersion, to normalize the variance. So the data are actually, let's say, scaled to zero mean and unitary variance. So this means this is quite strong, let's say, assumption and quite strong position, because we say that we give, let's say, equal dignity to let's say, equal importance to each variable. And this means that we also trust on this. These are the eigenvalues and of this matrix, or the matrix that we have seen before. So taking these, autoscale each variable, each column, then multiply this matrix by the transpose of itself, calculate the eigenvalues and the eigenvectors. This is the eigenvalues progression, and this is the variance associated, the cumulative variance. We see that the first eigenvalue, which is the largest, carries 40% of the total variance. When we had the second, we are more than 70%, 90% with the third. So we have, let's say, 6 variables, but actually with 3 of them, we cover 90% of the total variance. So this is, let's say, gives an idea of the correlation between between the variables, and then the correlation between what the variable means, namely the sugars, the acids, and so on. Let's suppose that we limit our representation to the first two, let's say, principal components. So we can, let's say, select PC1 and PC2, and we project from the 6-dimensional space onto the bidimensional space. And this is the arrangement of our data. Each point corresponds to one, let's say, of these cultivars. They have, let's say, fantasy names, but it's actually the commercial name of these cultivars. And each point is a different cultivar, and then we see that there is an arrangement of them. So there is a sort of similarity and differences between them. So we have this group clustered together, these are clustered together, and this looks very different from the others. But okay, how can we, let's say, correlate? How can we interpret this relationship, this, let's say, representation with the variable, with the original variables, plotting together the scores and the loadings? So I mean, plotting in this, that is the projection plane from the 6-dimensional space to bidimensional space of the data points. Now we are going to project also the axis of the vector space. And if we project the axis, we see that we have, let's say, these directions, and then we see how we obtained this representation. Because everything that is orthogonal in this space, it means that the original orthogonality of our space is preserved. So this means, for instance, that pH and sucrose are actually uncorrelated with each other. So we can have, let's say, acidity and quantity of sucrose, and this is not correlated with each other, because the orthogonality is maintained. Everything is orthogonal in terms of loading. This means that in the projection, the original orthogonality is maintained. But some other axes are, let's say, superimposed. You see, this means that in the projection, these two axes are go one of the over the other. This means that the quantity of glucose and fructose is correlated, and the same happens here from the quantity of acids, of citric and malic acid. So we have, of course, that the pH, that is the negative with respect to the concentration, is anti-correlated with the actual quantity of acid here, and this is basically the acidic direction. So these fluids are characterized by high concentration of acid, and this orthogonal is the direction, let's say, of sugar, and here we have, let's say, a biggest, quantity of sugar inside the fluids, and we also observe the sucrose is anti-correlated with respect to glucose and fructose. Sucrose is the disaccharide of glucose and fructose. So in these fluids that are, let's say, plotted far from the others, we have probably that the glucose and fructose did not give rise to the disaccharide. So it's still, there is, let's say, a different composition of the sugars. So this is something that we can infer from just looking at the principal components without knowing nothing, let's say, about the physiology of the fluid. But this is, let's say, a way to visualize the data and to interpret the data, also the data. But of course, we said before that here we are playing with the first two principal components. It means that there is 30% of what is in the data that is not, let's say, taken into consideration by this representation. And we can represent this, let's say, with this quantity, with the residual, let's say, measuring the difference between the original matrix and the matrix limited to the first principal, and what we have limited to the first principal components. And this is, let's say, the plot of the product of the score and the loading. So we can actually measure for each point which is the residual, namely the difference between the original data with all the variables, all the information, and the part of the information that is represented in the first two principal components. And we see that it is homogeneous, except in one case, this number 6, actually you see that looks very close here. It has a big residual. So this means that what we have said before, it holds for everything but not for this one. And this observation of the residuals is then very important, let's say, to interpret correctly the principal component analysis results. Okay. Now let's see another example about the gas sensor array. The gas sensor array I mentioned before is one of the, let's say, provides, let's say, a multivariate data, because from each sensor we extract one signal. Then for each sample we have an array of values, an array of signals. Now a gas sensor, a chemical sensor, provides a response, a signal that is the proportion, that is due to two terms, the quantity and the quality. So in the let's say in the signal of a sensor, here in case if it's linear, it's very simple. It is due by the product of the concentration times this term that is actually the sensitivity of the sensor towards this compound. So this carries the information about the quality, which gas is, and this carries the information about the quantity, how many molecules, which is the concentration of the gas. And this is quite, let's say, straightforward, but in some cases not considered, let's say, fact, because this means that we may have a very, very large sensitivity for one compound, but or a very small sensitivity for another compound, but if the compound for which the sensitivity is little appears at a very large concentration, we may have a large signal. And this is, let's say, the big problem when people try to develop selective sensors for something occurring at a very low concentration, because in the air there is a lot of other compounds at high concentration. Anyway, when we take, let's say, a measurement of different gases with an array. We have the space of the gases, so we have gas 1, gas 2, gas 3, and when we took into consideration the sensor space, and we see that the data are usually arranged in this way according to the mutual sensitivity. So we may have, let's say, arrays that can separate one compound from the other, but we have other compounds that are overlapped. So the sensors do not distinguish them. And this is an example of this. This is an array of quartz microbalances coated with different coating materials. And we expose these to several compounds, amines here, acid, and there are many compounds here. And each compound occurs at a different concentration. And what we have in the principal component is a structure like this. We see basically that here we have, let's say, many compounds, so we expect many lines, many vectors here, but actually what we see is two of them, one for the amines and the other for all the others, actually. Okay, and this means that this is due to what? This is due to the fact that sensors do not measure these compounds, or this is due to the fact that the concentration, let's say, is hiding what is here. So what we have a lot of correlation because the concentration, in some sense, creates this correlation. You know, the correlation in case of sensor arrays of chemical sensor is straightforward because each sensor is proportional to the concentration. So if the concentration changes, all the sensor changes in the same direction. There is a very simple way to observe this, because since this is linear, if this is linear, we can, let's say, remove the concentration in an array, simply dividing the response of each sensor by the sum of the responses of the other sensors. This means that since the correlation is common to each sensor, we can remove the concentration. And then this means that instead of using the data of the sensor, we use reduced data. Let's say each sensor is divided by the sum of the others, and this is what happens actually. So the correlation, the concentration effect disappears, and we can disentangle all the different compounds, and we can recognize all the compounds that were actually plotted one over the other here in this plot. Okay, and this is because let's say this is let's say an easy case where there is a linear relationship between the sensor and the concentration and the quantity of the measurement. And this makes a lot of sense because we have the chemical family distributed in this plane. We have amines in this side. We have here aromatics, alcohols, aldehydes, and so on. So when we go to plot the loadings here in this plane, we understand which is the contribution of each sensor. We have a sensor for alcohols, a sensor for amines, another for alkanes, and so on. So we can interpret this result, and we can, let's say, even understand which is the role of each sensor. And this is something that we can understood only in an array, not by the sensor itself, because each of these sensors is sensitive to all the compounds. It's just the interplay that provides these different contributions. Now, what is actually, in terms of the algebraic terms, the principal component analysis is a matrix decomposition. We have seen this before when we saw the residuals. Actually, we take our original matrix, n samples, n variables, and we divide them in the product of one score and one loading, the projection of the sample and the projection of the variable along the first PC, the second, the third, until the end. And if we cover all the n variables, we have n principal components, we exactly reconstruct the original matrix. And when we stop the composition to the first, the second, the third, and so on, we leave out some part, and what we leave out, what is it? Is the uncorrelated part. I mean that each principal component actually captures the direction of large correlation. Let me go, too much, sorry, here. You see, the first principal component is that along the largest, let's say, correlation between the sensor. And when we project along the first principal component, we leave the rest, and then we look for the maximum correlation of what we have left after the projection along the first principal component. It is the second, and then the third, and so on. So we are distilling the information, the variance in the sensor, taking into consideration the different, let's say, the amount of correlation. So we start with the X. The first PC is the maximum correlation. After the first PC, this is the maximum correlation direction, and so on. This means that at the end of the story, we leave the information that is not correlated. And in this information, we surely find the noise that is in principle uncorrelated. So at the end, in this residual, we find also the noise. And actually, the principal component analysis can be used also to, let's say, filter the data in order to remove noise. Let us consider, for instance, a collection of spectra. This is an experiment of reflectance anisotropy spectroscopy. Let's say is a technique where we are going to measure the reflected light when the incident light is polarized plus 45 degrees or minus 45 degrees. And it is a technique that can, let's say, give information about the arrangement of the film onto a surface. And here we have spectra of films of different heights, different layers of porphyrins onto a gold surface. And we have, let's say, this kind of spectra. We can treat this as a multivariate data because each spectra has, let's say, a number of channels. The correlation of spectra is very high because this point is part of a, let's say, of a spectral feature. So this point is correlated with what comes after and what comes before. So the correlation in spectra is very high. And then when we are going to calculate principal component analysis on this spectra, we have that the first two principal components basically carry about, the first three principal components carries about 100% of the information. So we have here 400, let's say, I don't remember how many, but there are some hundreds of spectral channels, but actually the actual dimension is 3 of this problem, is only 3. And then if we go to see which is the reconstruction of the data when we, let's say, decompose the different PC, this is what we get with the first principal component. You see, it's not very different from the original data, and it actually captures let's say, correlated part. So we have, let's say, an increase of this spectra when we go actually from one layer to another. Increasing the number of principal components, we find the spectral features that are, let's say, interesting. Correlated here means that they are found in any sample, and since the samples are the samples of the same molecule but at different layers, these are, let's say, important to describe this process of accumulation of the molecular film onto the surface. And this is what we have after the residual. So if we stop at this representation, so it's this minus this one. And what we have is actually the noise, basically. Probably there is something else, I don't know, but most of this here is the noise. So we have make a filtration of the spectra from the original to this one, and this is the part that has been removed. And actually, this is used, let's say, for this practical, for filtering data, the principal component analysis. A final application of principal component analysis is an image. If we take an image, this is the image of the molecular layers that have been measured with the technique that I said before. We have, let's say, grains, gold. This is an STM image. We have grains of gold, and these wrinkles here are the molecules, the porphyrins, the sapphirins, let's say, is a kind of porphyrin, a sapphire. That is, let's say, start to to grow at the border of the grains. We can treat this image as a matrix because this is a monochromatic image. It means that we have pixels. Each pixel has an intensity. So we can take the principal component analysis, and then we can take the principal component analysis first loading, the first principal component, at the second, at the third, and we see that increasing the principal component, the image is reconstructed. So we tend to obtain the same. But what is interesting is that what we capture in the first principal component are just the grains. You see that if we see this image here, the wrinkles, the molecule are practically not visible. And what we have is these very large patches in the images that are the grains. So we are, say, separating the two parts of the image, the grains, the big patches, and these wrinkles at the border. This is more evident if we consider not only the principal component, but the residuals. So the differences between the original image and what is captured by the principal components. And we see that the grains tends to disappear, and at the end we remain only with the wrinkles formed by the molecular fields. This is an example, let's say, of how to use principal component analysis in different kind of applications or contexts. Choose the timing. Okay, this was, let's say, the first part. The first part was the representation, the visualization of multivariate data. The second part is deal with the regression. So regression means from a measurement to estimate something that is correlated to that. And that depends to that. And this is quite straightforward in a univariate statistics. For instance, if we have a sensor V depending on epsilon, could be a strain gauge, for instance, we have a linear dependence on the strain gauge, but these are measured quantities, so we have errors. We have measurement errors, and this is the important part of the regression, because how to estimate, for instance, in this case, K in presence of errors, in presence of the fact that actually the data points are not aligned along a straight line. So if we take a couple of these and we tend to see for each of them, we tend to calculate K as a ratio between V and epsilon. For each point, we get a different value. And this is actually the balance between the theory and the reality, because actually what we have written here is what we think is the relationship between the signal and the epsilon. And we say this has to be linear. So this means that everything I see that outside the linearity is an error. Okay. If we do know errors, the existence of errors, and we say this, but probably here there is a very strange, highly nonlinear function connecting all these points. But of course, statistics does not make physics, and you have to know the physics and then to use statistics. Is not the contrary of this. And we know that this is used to calibrate, for instance, sensors. So we measure the V. This is changed into sigma, but this is an epsilon. And epsilon, let's say, is known. This means to calibrate, and then we estimate K. Then once K is let's say known. Sorry, this is known, and V is measured. We can estimate epsilon. So this is what we do with our sensors. And we know that this operation, which is the optimal K in presence of the errors E, random errors E, is solved by the least squares method. And we know that the least squares method means, let's say, to find the parameters of the function that minimize the square of the error. Of course, the method is based on some assumption. There are two assumptions that are quite important. The first one is that the uncertainty on Y, on what we measure, is much larger than the uncertainty of the known value. And since everything we know is known with certain uncertainty, this has to be in some way taken into consideration. The second assumption is that the measurements are normally distributed, and so we can calculate the parameter that maximize the probability of the observed quantity. And this is, let's say, the likelihood function, and the likelihood function is maximum when this quantity that is the least squares is minimum. So to minimize the error means to maximize the likelihood function, then to maximize the fact that what we observed is something with the maximum probability. So there is a sort of entropy principle in this story. And we know, everybody knows, let's say that with the linear function, we can solve the least squares, and we have the possibility to measure, let's say, the two parameters of a linear relationship, for instance. And this is, for instance, the case of a sensor sensitive to one concentration. Are the hypotheses valid here? So the error on the sensor response is much larger than the error on concentration. For instance, we have to be sure that the temperature is constant because this is a vapor, so it depends on the concentration, depends on temperature, or our mass flow controller is stable, and so on. It's normally distributed. The central limit theorem, let's say, give us, let's say, the plausibility of this. Are the observed events independent? This is also an important issue, least squares, when we do regression, and this means that each point is independent from the others. So it means that we have no memory. Our sensors are no memory, no hysteresis. And this means that to be sure of that, we should randomize the sequence and not simply increase the concentration. Then each measure has the same variance, is another assumption of least squares. If everything is done in the same instruments and so on, this is quite plausible. But this is the univariate, which is the passage to the multivariate, which is the next step. The next step is the solution of the least squares with the matrix formalism. We have that a matrix formalism for linear systems. If we have a system, let's say, of two equations into variable linear system, we can write this in terms of matrix, and the solution means to invert one of the matrix here, so A minus 1. We can do the same with the least squares. In the least squares, we have basically a redundant linear system, because each equation here, if this is the relationship, if we add a third one, it has to be linear combination of the others. But since we have errors, we can have, let's say, a number of equations independent one each other. So this means that we can no more invert, because this matrix is no more a square, is a rectangular, and the operation, the solution is provided by the so-called Gauss-Markov theorem that extend the matrix formalism of a linear system to least squares problem, introducing the pseudo-inverse matrix A cross. Is the extension, let's say, of the Gauss matrix, of the inverse to the rectangular case. So this means that we can increase the equation, means that we can increase, for instance, the number of observable, the number of sensors in our problem. So we can, let's say, have a variable as a function of many variables. We have many equations, more than the number of variables, because we have the presence of correlation and the presence of errors, and this can be solved by the so-called, let's say, can be solved by the Gauss-Markov theorem. I want to make now a little excerpt here to discuss if, let's say, let's suppose that we want to measure two compounds, M1 and M2, and we can choose to measure these two quantities with selective sensors. We adopt a sensor absolutely selective for M1, one absolutely selective for M2. What happens? That this space of measurements is transformed in the sensor space, and the area of the sensor space is simply the area of the measurement space times AB. But what is interesting here, of course, we can, let's say, is to understand how the error in the measure of S1 and S2 is reflected in the uncertainty of the estimate of M1 and M2. Actually, since we have errors, each axis here is not made by points, but is made by intervals, because what we can appreciate are intervals. because these are the intervals of our, let's say, measurement system that provide, let's say, a certain measurement error. So this area is actually tiled by these small tiles. And how many of them we have? We have, let's say, the area A, B, A, N divided by the product of the uncertainties, let's say the area of the single tile. And this means that when we go back to the original space, this means that we can appreciate a number of variation of the original measurement. It means that the smallest amount of variation of measurement, that is the resolution, becomes an area here because we have two variables, and this minimal amount is the ratio between the product, let's say, of the error of the sensor divided by A and B. What are A and B? Are actually the sensitivities of each sensor. So basically, we have the product of the resolution of the individual sensors. Is this the same when we have a non-selective sensor? I mean, if we have sensors that are contemporaneously sensitive to M1 and M2, what is the difference? Algebraically, we can calculate M1 and M2 from S1 and S2, in this case and in this case, without difference, without, let's say, any let's say, difference. But actually, the difference is in how the uncertainties are treated by this system with respect to this one. Because again, here, the error is still the same, delta S1 and delta S2. So the sensor space is again partitioned in a number of these small tiles. But is this domain that is changed? It is no more square rectangular domain. It becomes a parallelogram because there is, let's say, is a different system. And this area is no more the product A times B, but is the determinant of the matrix S times AN. So this means that when we are going to calculate which is the maximum variation of M1 and M2, so in how many partitions I can actually partitionate this space, this is something similar to what we had before, but instead of the product of sensitivity, we have the determinant of the system. So the determinant of this matrix actually plays the role of the sensitivity of the sensor. So this means that it's not equivalent. This quantity is large, let's say smaller than this one. We have to add the anti-diagonal terms. So this means that the resolution is in some sense larger. So this means that I partitionate this original space in a minor number of tiles. So the resolution of the two systems is not equivalent, even if algebraically we can, let's say, actually solve the system. Is it? So let's go back to our let's say, story, because now we can solve the problem as a multiple linear regression. So we can, let's say, calculate the matrix connecting the observable to what we want, to the variables of which we are interested. So this is, let's say, the formula, and this matrix B is the regression matrix, and it is calculated as y cross. This is the calibration data y cross times the, let's say, okay, here the calibration, the regression matrix is applied to y to estimate the value of x, and in calibration we can determine the value of this matrix B. And let's see an example, but let's see also the fact that we have a method to evaluate the goodness of the fit, and the goodness goes actually in the evaluating, let's say, the errors between what is fitted and what is real. Now we'll see examples of that. And let's see an example, for instance, with an array of 6 quartz microbalance sensors coated with different polymers, and they are let's say, sensitive to N-octane and toluene at the same time. And this is the plane toluene and octane. The red stars are the calibration points, and the red dots are the validation. So this means that we try to calculate the regression matrix on the blue, and then we apply them to estimate the the red one. And we see how good is the operation, going to see which is the difference between the estimation and the actual value of the test points. Okay, this is not so visible, but anyway, we have very simply for each of them, this is the sensor response, and this is the concentration of N-octane and the concentration of toluene. They are using mixtures, so we have, let's say, different characteristics because this is actually a function of two variables. This is the principal component analysis of the calibration, and this was the original sensor space, and we see that this parallelogram, because if we are going to connect the points for each, let's say, measurement couple, we obtain the parallelogram, let's say, not the square. You see that this is the 0, and then it is not, let's say, in a rectangular shape. If we apply the multiple linear regression, this is what we get. This is not bad, because we see that we can evaluate the concentration of octane and toluene. This is the so-called scatter plot. Here we have the estimated value versus the true value, and everything on the 45-degree line means is okay. And here we have 2% error in both calibration and test, 6% in calibration, 4% in test. So this means that there is a good, let's say, coherence between calibration data and let's say, the data and the test data. So this is a very nice example of multiple linear regression that it works, of course, when the sensors are linear. But there are limits to this, of course. First of all, there is the linearity. We assume the linear assumption. This is multiple linear regression. So this means that we have a linear relationship between, for instance, in this case, sensor response and, let's say, the concentration. But there is also another important limit, is the fact that the pseudo-inversion is reliable when the rank of the matrix is maximum. So it means when the sensor response are uncorrelated. This we have seen is not true. But here we have a method to solve, because there is a principal component analysis that say, don't worry if X is correlated, I can transform X to its principal components and then use this to calculate, let's say, the multiple linear regression. And this is actually done in a method that is called principal component regression. But what we are doing now is something more, a little bit ahead, because this is not the optimal choice of basis, because the principal components have been calculated maximizing the variance. Here we are interested to regress something value, let's say to retrieve some quantity. So we are interested, let's say, to find actually not a decomposition of the matrix in terms of variance, but a decomposition of the original matrix into directions that are actually correlated with the scope of our analysis. It means, for instance, in this case, the correlation. And this is actually done in advance of principal components. It's called partial least squares. This is an algorithm where there is an algorithm where we took into consideration the two matrices, the matrix, let's say, of the sensor response and the matrix of the concentrations, or the variables that we want to estimate. We calculate principal components in both cases. So this means that we have removed correlation. And then we rotate the representation in order to maximize the correlation between the scores of the sensor response, the sensor variable, with the scores of the variables that we want to estimate. And this is a great advantage, and this provides, let's say, a model that an algorithm very effective that can, let's say, solve many complicated problems. So we start calculating the principal components of X and Y, then rotation of the scores of one of them in order to maximize the correlation with the others, and then we can calculate let's say, make the decomposition of the matrix according to the number of components. And these are, when we make this rotation, they are no more coincident, let's say, with the principal component, and they are called latent variables. This is the term. Are no more principal components, but becomes latent variables. And again, we can decide how many latent variables we need to use in our system. And then this can be done, let's say, stopping the representation to a number of latent variables, evaluating the regression matrix according to the multiple linear regression, and then to predict our data. And what happens is the so-called overfit. So when we increase the number of latent variables, we have, let's say, we go to describe very, very well our calibration data, but at a certain point, the description does not work more for the validation, for the test set. So our PLS, the PLS method actually tends to completely recover the calibration data. So it is absolutely important to check this fact. So to calculate the error on calibration versus the number of latent variables, and to calculate the error, let's say, on the validation test set, and to stop, to have an optimal point when we reach, let's say, the good, the best performance on the validation, because we are not interested, of course, to estimate the calibration data, because they are known. We want to use this to evaluate, to estimate in case of no unknown samples. And how many? 5 minutes. So I discuss this one because it gives us, let's say, more information. This is, let's say, the near infrared spectra of diesel fuels. There is a number of diesel fuels, and for each of them, we have some properties measured with another instrument. Boiling point, the cetane number is the combustion speed, the density, the freezing temperature, the flash point, which is the lowest temperature to form, let's say, an ignitable mixture in air, the total aromatic compounds, the mass fraction that is due to aromatic compounds, and the viscosity. So these are the properties necessary to let's say, evaluate the quality of a given fuel. And this is the near spectra from 750 up to 1.6 microns. And here we have, let's say, done with one instrument, a near spectrometer. And this is the variability of the different properties. We see that there is a quite a good, let's say, the distribution from which they come is quite homogeneous. It's not too relevant, but anyway. And what happens if we apply the multiple linear regression? So the method that worked so well with the array of quartz microbalance. Here we have again the blue is the, let's say, is the calibration data points, and the red are validation. So for the blue, we provided to the method both the spectra and the properties. For the red, we provided only the spectra and say what is the properties, and then we checked which is the difference between the estimated and the real value. And we see that except density and aromatic, we have, let's say, very bad estimation of the other quantity in test. Very good on calibration, of course, because it overfits. It doesn't take care, it doesn't control the overfitting, and it works very well with density and the total aromatics. But this is quite simple because it is quantitative. So I mean, if there are more aromatic compounds, there are more largest spectral features due to aromatic compounds. If it is more dense, there is more molecule inside, so the spectra is correlated to that. But it fails in the other cases. So let's consider the PLS. If we take, let's say, PLS model from the same spectra, but to evaluate the different compounds, we see that for different compounds, we need, let's say, a different number of latent variables. it goes from 30 to 15, something like that. It depends, let's say, on the relationship between the properties and the near spectra. And this is what happens with the PLS. So it's much better than before. And we have, again, very good on density and aromatics, but we are also very nice, very good estimation, for instance, for boiling point, viscosity, not so good for the flesh, but in any case, this is one instrument replacing 7. So this is quite, let's say, interesting example. Now we can ask what is actually the contribution? What happens, or best, what happens to the regression matrix when we increase the number of latent variables? So let's take into the consideration the last case, the viscosity. So it is not perfect, but not bad. So here we have the relation, what happens in terms of estimated value versus true value. In case we stop the PLS to the first latent variable, you see very bad in both cases. The second latent variable still very bad. When we introduce the third latent variable, correlation between estimated and true value starts to occur. You see that the data tilts start to be oriented along the 45 degrees. As we go ahead, we have a shrinking of the data along the 45 degrees line. So it means that it's going quite well. And here we see the numbers, the errors from 17 drops to 12, to 10, to 12 again, then to 6. And then we reach the plateau, the minimum, 6, and then it increased to 9. So this means that here, and actually with the viscosity, we found something around 18, the value, the optimal value. Here we are between 10 and 20. So this is just to show a few examples. Okay? And we can ask of what is done the regression matrix. And we can see this here. The blue is the typical spectrum of the gasoline, of the fuel, and the red are the components, the elements of the regression matrix. And you see that the first latent variable is just proportional to the spectrum. So this means that each point of the spectrum is taken into consideration, and according to its value, it's used in the regression matrix. When we increase the number of latent variables, you see that starts to happen something. We see something like a derivative here. You see that this peak and this red shape is just the derivative of the peak. But the derivative is done not everywhere, but only on the peak, on the relevant part, and so on. Going ahead, we increase, let's say, this up and down, this derivative shape. So at the end of the story, we understand that PLS as a combination of first order, second order, third derivative, and so on, as a sort of a linear, let's say, as a sort of very similar, not the same, but very similar to a Taylor expansion of the function. So we're going to consider the derivative of the part of the relevant part of the spectra, but not everywhere, but just in those parts that are actually correlated with what we are looking, in this case, the viscosity. I think we can stop, can stop here. And just a final sentence, principal component and partial least squares are just the bottom. You can build over that. There are neural networks, biomimetic circuit, algorithms, and so on. But nonetheless, this is the basic, and this is what you provide, let's say, the control. So you can understand how individual variables affect your final results. Even if, in some cases, using neural networks and so on can provide you a better estimate, here you can actually control what's happening. Thank you.